So welcome to Math 150, Multivariable Calculus, Lecture 3. So today we're going to be doing dot products, law of cosines, determinants, areas, maybe a little bit of vector cross products. We can define anything we want in mathematics. Most definitions are worthless and are not valuable items to study. Certain key ones are. And the question is, which are the objects that are worth studying? So two of the big ones are dot products and cross products. These are ways of taking vectors as inputs and getting new objects as outputs. With the dot product, if you take two vectors in, what does the dot product give you? What kind of object? It gives you a scalar, it gives you a number. If you take the cross product, you take two vectors in, and what do you get as an output? A vector. And so the cross product sadly does not exist in all dimensions. It exists in 3 dimensions, and because of that, we have some shortcuts for things, which is wonderful. The dot product exists no matter what dimensions you have. The formula for the cross product is often unlikely when you look at it. And every now and then there are things in life that you just have to memorize. Your multiplication table, this should be memorized. Or do everything in base 2 and multiplication is a lot easier. There's just some things that just have to be hardwired. Now there's tricks to do a lot of this, like the determinant. If you put in ijk for the first row and then your 2 vectors, and you expand that, that actually gives you the cross product. It's a nice mnemonic. All right, so what I want to talk about first is the dot product. We have v dot w is v1 w1 plus vn wn. It's the sum, k goes from 1 to n, of vk wk. And so if we were to draw them, here's v, here's w, here's the angle. I could give that angle a better name. I could call it theta sub VW. Given that the only vectors in play right now are V and W, and the only angle in play is this, I don't see the need to have this overly burdensome notation. But if I had multiple vectors going on, well, which angle am I talking about? If I have a subscript VW, I'm talking about this one. Okay. And so the theorem is that v dot w is the length of v, the length of w, times the cosine of the angle between them. So there's real content to this. The definition of the dot product is just this expression. The content is that this is equal to the length of v, length of w, times the cosine of theta. On a related note, the fundamental theorem of calculus, we don't use the word fundamental lightly. You have not seen that many fundamental theorems. Can anybody give me a fundamental theorem you've seen? Probably only 2. There's the fundamental theorem of algebra. A polynomial with complex coefficients of degree n has n roots counted with multiplicity. And there's the fundamental theorem of arithmetic. Every number can be written uniquely as a product of primes in increasing order. The fundamental theorem of calculus is if I have some function f of x, and the derivative of big F is little f, so big F is any antiderivative, then the area under y equals f of x from A to B is f of B minus f of A, and we write integral from A to B of f of x dx. If you do not use the word area, I will be very upset. Which superhero has the catchphrase, "You wouldn't like me when I'm angry"? Hulk, excellent. Right? This is worse than rooting for the Yankees. Because if you don't put in the word area, it's a definition. If you're just saying the integral from a to b of f of x dx is big F of b minus big F of a, you've just defined a quantity. The content is that the area under the curve is the antiderivative at b minus the antiderivative at a. That's the meat. So you have to include area. So this is the big result from Calc 2. And this is one of the reasons why we care. It turns out areas are often related to probabilities. And that's one of the reasons why this is so useful. So coming back here, the content of this is that I can express the dot product in terms of the length and the angle. Now, the proof that I gave in the previous video used the law of cosine. And the way the law of cosines worked is maybe here was the vector v, I think I used p and q, here was w. And then if these two are going to add up to v, this has to be v minus w. And then we needed the law of cosine, so we always would like to draw right triangles. And so if I call this length A, and this whole length B, if I call this C, if I call this X, if I call this B minus X, if I call this H, I have two different right triangles that involve H. So I get H squared is A squared minus X squared from this triangle. And I also get H squared is C squared minus B minus X squared. And now just when you solve for C squared, and you note that X is equal to A cosine theta, after some algebra, which I urge you to do, you'll get C squared is A squared plus B squared minus 2AB cosine theta. And that is a proof of the law of cosines. What would be a really good value of theta to test this on? So 0, but if it's 0, it's going to be flat down like this. But that's definitely a test you could do. So if we take theta equals 0, then C and A should add up almost to B. And it's going to be a completely degenerate triangle. Not 45. What's the best value of theta to take for cosine of theta? 90. What's the cosine of 90? So if theta equals 90, then this just becomes the Pythagorean theorem. C squared is A squared plus B squared. So it's a special case. It's not a proof that we haven't done any mistakes, but it's nice to be able to check special cases. So check theta equals 90 degrees, or pi half radians. So that's one way to prove this. What I want to do now, since that proof was done in the lecture, and that's the proof that's done in the books, I want to give a different proof today that really highlights what's going on and shows you why something like this should be true. The first thing is whenever you see a formula, you want to try to sniff out its behavior and see, is it reasonable? So if I look at the formula, if I double the length of V, what happens to the right-hand side? We have V1 W1 plus Vn Wn equals the length of V, the length of W, cosine theta. If I double the length of V, what happens to the right-hand side? It doubles. What happens to the left-hand side? So if I double the length of V, I've multiplied every component of V by 2. So what will happen to every summand here? Double. So is it still going to be true? If I triple the length of V, I triple the right-hand side, I triple the left-hand side. It's very reasonable that in a formula like this, I should have a length of v on the right-hand side. That's a reasonable term. Same thing by symmetry for w. For the angle, I can't really tell which way it's going. If you want, without loss of generality, what can I assume about the length of v and w? The length of v equals the length of w equals. So if it's 0, then I collapse them to a point. So I can rescale. What value would you want v and w to be? 1. I can assume that v and w are on the unit circle. I can always adjust so that they have length 1. And so when I'm trying to prove a formula, this allows me to have simpler algebra, simpler numbers to work with. Is there anybody here who was not born in a country that uses the English system of measurement? Is there anybody here who is naturally metric? Okay, so how warm is it today? Right, and so for me, as soon as you say 5 or 3 degrees, it doesn't mean anything to me. I have to convert this to Fahrenheit. Is it hard to convert from Celsius to Fahrenheit? We have a very nice formula. Right? It involves adding 32, it involves multiplying by 9/5. There's a nice formula that allows us to go back and forth from one to the other. It doesn't really matter which one I use. It's nice to be able to convert things to having things of unit length because I have a simpler way of writing things. I can now regard v and w as being points on a unit circle. And again, you have to imagine that I'm drawing things like circles. So imagine here's v and here's w. So there's a lot of ways to do this. The simplest, of course, is what would be the nicest place to have v? Along the x-axis. So let's assume v is along the x-axis. And here's w. This is the angle theta. So v is going to be the point 1, 0. What would the coordinates of w be? Yeah, we just come down here. This is cosine theta. This is sine theta. And so in this special case, v dot w is just going to be cosine theta. I am not proving the dot product formula that v dot w is length v, length w, cosine theta in full generality. I am concentrating on the plane, and right now I'm even doing the special case when v is at 1, 0. I'm doing this to try to build intuition, to try to help you see how you would attack problems. Isn't it much nicer if one of the vectors is lining up with the coordinate axes? This is what you do in linear algebra. All linear algebra, or at least a huge amount of the subject, is choosing the coordinate system that makes things nice. Well, let's consider the more general case. If this is theta, well, here, let's use, this is angle A, and let's say this is angle B over here. The coordinates of B would be cosine A, sine of A, and W would be cosine A plus B, sine of A plus B. And again, I'm assuming that A, B, and A plus B are all in the upper right quadrant, just to make the algebra nice. I'm just trying to do a simple calculation. Can we take the dot product of these two? Yeah, the dot product would just be cosine A plus B times cosine A plus sine of A plus B sine of A. What's the angle between them? B. And so I would have to see, does this equal the cosine of B? Because I would have to start playing with trig identities. Is it possible to play with trig identities? Yeah. You know, the more math you know that's prerequisite, the more you can do with stuff like this. But what you really want to do is you want to try to find a good way to represent things. And so what I want to do is I want to talk a little bit about matrices and give you a little bit of a precursor to what would come next in linear algebra, and so that you can see the benefit of writing things. So, has anybody not seen matrices before? Matrices acting on vectors, 2 by 2 matrices. So you've hopefully seen these in solving systems of equations. I have some matrix acting on x, y, and I want to often find the inverse of the matrix and stuff like that. So what I can do is I can look at a matrix called R theta is cosine theta, sine theta, minus sine theta here, sine theta, cosine theta. This is a nice 2 by 2 matrix. And we can ask, what does this matrix do to the coordinate axes? If I take our theta and I have it act on 1, 0, all right, so I have cosine theta minus sine theta, cosine theta, acting on 1, 0 is going to be cosine theta, sine theta. What I've done is I've taken the vector 1, 0, and I've moved it theta. You can have of theta act on 0, 1. It's going to be a very similar calculation. So I take my matrix, and I act now on 0, 1, and I'll get minus sine of theta, cosine theta. That takes the vector over here, and that moves that by theta. What do you think this matrix does to any vector? Yeah, rotates it how much? Counterclockwise by theta. So the effect of this matrix is to just rotate you by theta. I did this for 2 special vectors. I did it for pointing in the x direction, pointing in the y direction. You can do the algebra no matter where you're pointing, it rotates you by theta. What do you think would happen if instead of theta I put in 2 theta? How much would it rotate you by? 2 times theta. How would you undo a rotation of theta clockwise? What matrix would undo this? Yeah, so if we look at R minus theta, that would be cosine of negative theta. Cosine is an even function. So what's the cosine of negative theta? Cosine theta. An even function doesn't care about minus signs. Sine is an odd function. So what is sine of negative theta? Negative sine, so the 2 negatives cancel, and it becomes sine of theta. And you would have negative sine of theta and cosine of theta. And if you do the calculation of theta of negative theta, you get the identity matrix, and you really do prove that they undo each other. Any questions on what we're seeing? So the whole point is r theta moves you by theta radians. We know how to prove the law, the dot product law, if one of the vectors is lined up with the x-axis, right? If it's lined up with the x-axis, we saw that the proof wasn't so bad. So in general, if I have something like this, what should I do? Yeah, just rotate it down so that the v lines up with the x-axis. Is that going to change the angle between them? No. So this is another way to try to prove the dot product theorem, that v dot w is length v, length w, cosine of theta. We first say, we might as well assume the lengths are 1 so that they lie on a unit circle. And now what we can do is we can just go through and do the algebra. Again, it is absolutely fine if you are not following every line here. This is meant to just give you a sense of what happens if you continue in mathematics. This is meant to give you another way of looking at things to see the connection, and to just emphasize the power of looking at things the right way. This is the simplest problem. I want to do the simple problem. Do the simple problem first, build up your intuition, and then show that anything can be reduced to the simple problem. So all we have to do is say, well, what would happen if we have two general vectors and we rotate them? Oh, let's do it like this. So let's say we have V is V1, V2, and W is W1, W2. We can now rotate so that we move them to the, we move one of them to the x-axis, or we can start with something on the x-axis and rotate up to these. It doesn't matter which way we do these. I'm checking if I did anything in my notes. Right. So we can look at r theta of v and r theta of w. And then we want to look at their dot product. So these are going to be two new vectors. And so when you go through and you do the dot product, it turns out that this is useful notation. Have you seen the notation with the transpose? Okay, so some yes and no. So if I give you a vector v is v1, v2, I'm writing it as a column vector. The transpose just makes it a row vector. So v transpose would be v1, v2 would be a row vector. Has everyone here seen matrix multiplication in Algebra 2? 2 by 2 matrices, matrix after one vector. I go through one. This is one of the reasons why I want to review it. There are some classes that do a year-long linear algebra multivariable calculus combination course. Because when you know linear algebra, the language is a lot easier. What do we mean when we want to take the dot product of two vectors? Well, if I write one of them as a row vector, v1, v2, and the other one is a column vector, w1, w2, if I do the matrix multiplication, it's v1, w1 plus v2, w2. So another way of viewing the dot product is it's just v transpose w. And that's what we mean when we say take the dot product of two vectors. Have one of them as a row vector, one of them as a column vector. So it turns out if you have a matrix acting on a vector and you take the transpose, this is the same as v transpose a transpose. And so what does it mean to take the transpose of a matrix? If A equals A, B, C, D, then A transpose is A, B, C, D. So now, if I actually do the calculation, if I do R theta V, I take the transpose of that, it's V transpose R theta transpose. It's V transpose, and then it's going to be cosine theta minus sine theta, cosine theta. And that's just V transpose R of negative theta. Yes? So this is just how this is to make things work out. And so it's a good question. If I just go through and put in my matrix A, V1, V2, and compute that, and then I compute this over here, these two expressions will leave. So when you take the transpose, you switch the order. And this is just how matrix multiplication works. And this is always, a difficult choice as to how much of this do I want to get into. But the idea is if I do this, I switch the orders. Notice that this is R of the negative theta. And so if I now put everything in here, if I have R of theta V transpose R of theta W, this becomes V transpose R of negative theta R of theta W. Oh, look, I take W, I rotate by theta, I then undo the rotation by theta. Well, what happens if I rotate by theta and then I undo the rotation? You end up where you started. So this is just V transpose W. And this is the proof that the dot product is not going to change if I rotate. So this is an advanced proof. It is absolutely fine not to understand all the steps, but at a more fundamental level, this is telling you what's going on. Is the dot product is unchanged as we rotate. Which makes sense. The dot product, well, the angle is clearly unchanged as we rotate, right? If I rotate V and W by the same amount, I can't change the angle between them. It's not at all clear when you look at V dot W, V1, W1 plus V2, W2, that's not going to change as I rotate. That's much harder. But the idea here is that if you view things the correct way, it's not so bad. Build your intuition from special cases. If you can't even prove things in a special case, you have no chance in general. If we can't even prove the formula when one of our vectors is along the x-axis, good luck in general. So let's do that case first. Let's build intuition. This is similar to what we were doing for the product rule last time. So we start off with functions we knew. And so this is another way of looking at what's going on. The other way is just the law of cosines and then just doing all the algebra. There are some math charts that have a professor at a blackboard with a lot of scribbles, and then it says, and then a miracle occurs, and then you have the answer that you want. When you look at the algebra, it's often sometimes hard to see why is it true. I did the calculation, I followed it line by line by line, but why is it working? And the reason it's working is here is the higher level approach. Any questions either on this or just on the dot product formula in general? So the dot product formula is extremely valuable. The next thing is the formula for the determinant. And again, when you take linear algebra, if you take linear algebra, you will do all of this again, and you'll have a better language for understanding what's going on. I'm trying to give you a little bit of a heads up in case you go on to linear algebra, which is the next class to go to. I'm going to, for the most part, focus just on proving things in the plane, and just try to argue that you can do more involved calculations in general. So the determinant is a little bit more complicated than the dot product. And for the determinant, order map. For the dot product, if I switch the order of V and W, that doesn't change anything. This is more similar to the area under a curve in calculus. If I integrate from 3 to 5, that's the negative of integrating from 5 to 3. If I go backwards, I reverse, I put in a minus sign. And so if you are ever asked to calculate the area of a parallelogram, it's not the determinant that you have to calculate, what you have to calculate. Not the cross product is related to the determinant. If I ask you for the area of a parallelogram, what kind of number is that? I'm sorry? If I tell you something is an area, what kind of number is an area? Almost. A little bit positive or zero, it's non-negative. So if I calculate a determinant, determinant gives you the signed area of the parallelogram. If I switch the orders of of the two vectors, I change the sign. So if I want the area, it's not the determinant that I calculate, what do I calculate? The absolute value of the determinant. So if I have V and W, here is V plus W, and I can calculate the area of the parallelogram. So the signed area is the determinant V1, V2, W1, W2, which is V1, W2 minus V2, W1. And then you can calculate the signed volume of a parallel piping where I would have another thing coming out. And so I'm going to focus on just the two-dimensional case. So when you look at this formula, you always want to ask, is this reasonable? What should happen to the area if I double V? What should happen to the area? It should be double. What should happen to the area if I triple V? It should be triple. Notice that each summand has exactly one V. So if I double V, I double this, the area doubles. If I triple V, I triple this, I triple that, the area triples. This is a reasonable formula. Same thing for W. So, without loss of generality, what should I assume about the length of V and the length of W? I claim it's sufficient to study just a special case when the length of V and the length of W both equal. Sorry? 1. I can always adjust unless there's one case when I can't adjust on having length 1. What case would that be? Yeah, if one of them has length 0, I can't rescale it to have length 1. But if V has length 0, what must be true about V1 and V2? What's the only vector that has length 0? The 0 vector. So if one of my vectors is the 0 vector, I already know the formula. So without loss of generality, I can just consider the case when V and W have length 1. I can handle the other case. If you could control the universe, which direction would V point in? Yeah, you would have V would just be the vector 1, 0. And now, here is W, and if this angle is theta, W is cosine theta, sine theta. So if I want to calculate the area of the parallelogram, I need the height. What is the height going to be? The height is just going to be sine theta. And so now, the signed area is going to just be sine of theta. And if we look at the matrix, it's 1, 0, cosine theta, sine theta. And if we take the determinant, it's 1 times sine of theta plus 0 times cosine theta, which is just sine of theta. Does this prove the formula? No. This proves the formula only in the special case when one of our vectors is pointing in the x direction. What should we do if it's pointing up by theta radians, or by phi radians, or by q? What should we just do? Rotate it back. And so I spent some time this morning, writing the mathematical code. And so I'll hold it up like this. I have no idea if this actually can be readable. And I will send this out later. And so you can actually go through and you can do it, and you can get excited. You can use the trig formulas for sine of a minus b. I have a small amount of psychic powers. I can read minds a little bit, and I am not sensing anybody who is praying, please have Professor Miller do the algebra right now. If I am wrong, email me privately, and I will set up a time to talk to you about the algebra, or I'll write it up and send you the write-up. I don't think it's the most productive use of time to go through this. What I hope you realize is how, by using rotation, we were able to go through and do the calculation. I may not have followed every step, but I kind of saw that if we rotate things, we can reduce to that special case. We can probably do something similar here. And we'll just see that the expression doesn't change when we rotate. And it's just a little bit of trig algebra. And so at the end of the day, we get the formula for the determinant is going to be the area. And we build our intuition on the simple case. The more general case is just coming from, trying to write, well, if this is V and this is W, then I want to find this length over here. And this length over here is going to be the length of W sine of theta. And now the hard part is, how the hell do I express sine of theta in terms of the components of V and W? So this is a general principle in mathematics. Depending on what you're given, that's going to influence how you do things. One of my favorite quotes, and if I ever get a shield, it will have a hammer on it. Does anybody know the principle or the law of the hammer? If all you have is a hammer, pretty soon every problem looks like a nail. And there's a lot of ways to look at this. One way is, if you're good at something, and whatever anybody gives you, you find a way to convert it to what you're excellent at. If you listen to any candidates debating, it doesn't matter what question they're asked. After about 30 seconds, they move into their set speeches they were going to talk about no matter what question is asked. There's another way to look at the law of the hammer. Go to the land of the screwdriver. If they could have solved the problem using screwdrivers, they would have. They're smart people too. They would have used their techniques. So the great Richard Feynman, Nobel laureate in physics, a phenomenally original person. He had a reputation for being phenomenal at integration. And he got this at, I think, MIT and Princeton, undergrad MIT, grad student Princeton. And people would often come to him with integrals that they were stuck on. And Feynman would look at it, go, here's the answer. Wow, how did you do it so quickly? And so one of his books, he actually talks about his secret. And the secret is, I'm at MIT and Princeton. The people around me are smart. If you could have solved the integral using the standard technique, they would have done so. So clearly, it's not worth my time to try any of the standard techniques, because if they could have done it that way, they would have, and they wouldn't be asking. Most people don't know the integration technique differentiating under the integral sign. Let me try that first. And you would have tremendous success with that. So if you have a different skill set than other people, take advantage and work in that field. I've published papers in geology, in economics, in statistics, in sabermetrics, in marketing, in physics. There's so many different fields. You can move math to so many different things. And if any of you are interested in trying some projects, let me know, because I have There's several that are accessible to undergraduates. And so the idea is we know things about the coordinates of V and W. We know the dot product. The dot product involves cosine of theta. Are there relations between cosine theta and sine theta? Yeah, what's a good relation? Good, cosine squared theta plus sine squared theta equals 1. So if I have a sine of theta, I can write that as the square root of 1 minus cosine squared theta. And I can write cosine squared theta in terms of the dot product divided by the lengths. And so then the idea is maybe if I just do a bunch of algebra, at the end of the day, things will work out. It's a little bit unenlightening sometimes to do the algebra. And just, when things happen at the end of the day, great, you have the formula, but you don't necessarily have the higher level understanding of why it's true. And I'll talk more about that later in the semester, but right now I just want to give you a sense of why this formula is true. In a linear algebra class, you'll do a better job of explaining why it's true, not just for the plane, but for 3 dimensions and higher. For the most part, we're not really going to be doing things in 4 dimensions and higher. We will be doing some things in 3 dimensions. Now, when you talk about the area, if I specify V is in this direction, which direction for W will make it the easiest to calculate the area? One is 90 degrees, because then it's just a rectangle. And there's another direction that's going to be very easy to calculate the area. So one is if they're perpendicular. What's the other choice? Parallel. So if W is in the direction of V, what should the area be? Yeah. And so you can check. So let's say we have V equals V1, V2. And let's say W equals alpha V1, alpha V2. So it's in the same direction, it's just been rescaled. Now if I look at V1, V2, alpha V1, alpha V2, I will get V1 alpha V2 minus alpha V1 V2, which is 0. So the claim that this formula gives us the area is at least a reasonable claim. So whenever you can do smell tests like this, you should. And just see, is this reasonable? One of my students from Brown years ago was working in an investment company, and just something didn't look right. He did some quick tests, and it turned out a minus sign was dropped somewhere. And he was able to just quickly look at the formula and see, this isn't quite right. I was taking a thermodynamics class as an undergraduate. What happens if you throw an ice cube in a pool? We actually had the pool freeze. So obviously there was a minus sign somewhere. You should not have the entire pool freezing from throwing in one little ice cube. You want to be able to look at the answer and say, is this reasonable? So whenever you can check special cases, check special cases. Okay, so there's a lot more that we can do here. So determine the basic areas. If I have 3 things, it would give you the volume of the parallel pipe. And there's a lot of different vector analysis formulas. A lot of these formulas can be proven by brute force. So if I give you V1, V2, V3, W1, W2, W3, U1, V2, V3, I can calculate what's being done by here is U, is V, maybe here is W coming up, and try to calculate the volume of the parallel pipe. And there's a formula for this in terms of dot products and cross products of the 2 quantities. And if I tell you what the formula is, you can often prove it by just doing long, unenlightening algebra. And there's a whole slew of different formulas you can do. Some of the formulas are intuitive. If I do V cross W, this is negative W cross V. This is very different than V dot W is W dot V. And if you think about V dot W, what is this giving us geometrically? It's giving us the so if you want to assume V and W are unit vectors, what is V dot W giving you? This was the first thing we did today. What does V dot W equal? No, just in general, V dot W, the cosine of the angle. And the cosine of theta is the same as the cosine of negative theta. Cosine is an even function. So V dot W should be the same as W dot V by our theorem. If I take the cross product, this is giving us the sine area of the order matter. If I go back to the original problem over here, if instead I did cosine theta, sine theta, 1, 0, I would now get negative sine of theta. If I switch the order of the two vectors, I now have a negative for the value. So the cross product, it turns out, involves a signed quantity. If this is V and this is W, this is the right-hand screw. The way you figure out where V cross W is a vector that's perpendicular to both V and W. And it comes out of the plane. And the way we figure it out is we have our hand, we take our right hand, we align our hand with V, and we curl it towards W, and our thumb points in the direction of the cross product. This is just really good notation, so that you can quickly figure out which way things are going. If I then do W into V, I would start here, twist my hand, and now you see I'm pointing in the other direction. So W cross V would be going into the black hole. In physics, you often have like the electric field and the magnetic field, and then the cross product of them is the direction of electromagnetic propagation. It's called the pointing vector. Do you know why it's called the pointing vector? Yes. And when we heard this freshman year, we thought it's the pointing vector because it points in the direction of motion. But the guy's name was pointing P-O-Y and T-I-N-G. It's one of the few people where you're clearly not going to have your name dropped from the object, because the name just fits so nicely. So V cross W is going to come out like this. What should the dot product of V cross W be with V? If you're coming out here at 90 degrees. Zero. So check. V cross W dotted with V should be the scalar 0. There is a way to prove this by pure algebra. I write down what V is, I write down what W is, and I go through and I do the calculation. And if I do the calculation at the end of the day, when the dust settles, I will get 0. The reason I'm getting 0 is V cross W is a vector whose magnitude is the area of the parallelogram spanned by V and W, and pointing in a direction that's perpendicular to both. Oh, it's pointing in a direction that's perpendicular to both, then its dot product with V has to be 0. And this is the advantage of the dot product formula, that it's length of V, length of W, cosine theta. If theta is 90 degrees, cosine of 90 is 0, so two perpendicular vectors have a 0 dot product. So if the dot product is 0, they're perpendicular. If they're perpendicular, the dot product is 0. But you can prove this by just doing a lot of algebra. It's not fun. And so I, J, K, P1, P2, P3, W1, W2, W3. The mnemonic to remember the cross product is you just write the first two columns again. I hat, J hat, P1, W1, P2, W2. And you have these ones all coming in with a plus sign, and these ones all coming in with a minus sign. In some sense, this is terrible notation. I have a matrix, and two of the rows of the matrix are just numbers, but the first row is actually vectors. I have the unit vector in the x direction, unit vector in the y direction, unit vector in the z direction. But when I do this out, I get I hat v2w3, then I have plus j hat v3w1 plus k hat v1w2. Then I have the minuses, it'll be minus, I'm always going to write the v's first. I have a minus k hat v2w1. Do I want to write that over here, the minus k hat? Where do I want to write the minus k hat? Yeah, that's this one over here. Minus k hat v2w1. The next one is going to be a minus I hat v3w2. And then a minus j hat v1w3. So I can do this as a vector. It'll be v2w3 minus v3w2 is the first component. The next component is going to be v3w1 minus v1w3. And then the last component is going to be v1w2 minus v2w1. You can memorize this formula, or you can just remember this expansion and derive it that way. Either way is fine. Do you notice anything interesting about the components? What do you notice about the first component? It doesn't have a subscript one. What about the second? Does that, what about the third? Okay, good. So this is going to help me memorize things. Each component is missing the corresponding subscript. And it goes in order. It goes 2, 3, then 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. The difficulty is remembering which thing comes first. Well, I'm going first with a 2, then with a 3, then with a 1. I'm basically wrapping around on a circle. First subscript is missing, so I start with a 2. Second subscript is missing, I start with a 3. Third subscript is missing, so I start with a 1. And so if you can remember that, you're in great shape. This is going to be v cross w. And now, if I take v, which is v1, v2, v3, and I take the dot product, I get v1, v2, w3 from this. And then v1, v2, w3 minus v1, v2, w3. Those cancel. And so you can start to see as you do the algebra that things are going to cancel in pairs. And with a little bit of patience, you will go through and you will see that v cross w really is perpendicular to v, and it really is perpendicular to w. If you think about this, if I give you a vector here, and I tell you something is perpendicular to it, that gives you a plane in which it can live. So how many dimensions does a plane have? 2. So if it's perpendicular to v, it lives in this 2-dimensional plane. But it's also perpendicular to w. So it lives in that 2-dimensional plane. So now you get these 2 planes in your mind, which will be played by these 2 pieces of paper. In general, if 2 planes intersect, what are they going to intersect on? A line. And that line is going to be where v cross w lives. It's going to live in the intersection of the 2 planes. So this gives you a little bit of an idea of the geometry. This is something that is truly remarkable and nice about 3 dimensions. If I give you 2 directions and they're not parallel, then the 3rd direction is all I need to uniquely determine where things are in the universe. Okay. So these were basically the things I wanted to talk about today. The real key takeaway here is the power of looking at a good special case and building things up from that. Any fans from Friends? Any fans of the Friends TV show? So I didn't watch it initially, but my wife and I started dating and getting married right when Chandler and Monica were doing it. So the episodes had interesting impact. Every episode of Friends, but two, the title of the episodes begins the same way. If you haven't really seen the show, you're probably not going to know this. Every episode but two, I believe, the title begins the one with. And so eventually in the semester, we will prove the fundamental theme of calculus. And I titled that lecture, The One With the Mean Value Theorem. The mean value theorem is one of the most important theorems in calculus. And it basically says that if you have a continuous differentiable function, that at some point, your instantaneous speed equals your average speed. This is a no-shift theorem. To give the language. Imagine your average speed is 50, but you're always traveling below 50 miles per hour. Could your average speed be 50? No. What if you're always traveling above 50 miles per hour? Could your average speed be 50? So as long as your speed is continuous, as long as there's no gaps, so that's the intermediate value theorem, that there's no gaps with a continuous function. If you start at 20 and you end at 80, you have to hit everything in between. So the intermediate value theorem essentially gives you the mean value theorem. So how many of you have seen the mean value theorem in calculus? Mean value theorem would be f is continuous, differentiable. There is a c in the interval ab such that f prime of c is f of b minus f of a over b minus a. So this is the mean value theorem. There's a special case of the mean value theorem that you might have seen. Anybody know the special case of the mean value? I'm sorry? No, the intermediate value theorem actually leads into the mean value theorem. The intermediate value theorem just says you hit all intervening points, but this is not transporters from Star Trek. There's a special case. Yes. When f of b equals f of a, and what do we normally assume that they equal? Well, we can just translate the function up and down. So if they're going to be equal, what should we set them equal to? 0. So in this special case, when you're 0 here and 0 here, it says there's at least one point where your slope is 0. Anybody remember the name of this theorem? This is Rolle's theorem. The more general case so here's the more general case of the mean value theorem. Everything I've been telling you is about looking at things the right way. When you look at this function over here, we're using Rolle's theorem, the average speed is 0. Here the average speed is not 0. Do you want to choose your coordinate axis like this, or do you want to change your coordinate axis? Yeah, where should you put the center of your coordinate axis? We have it here. Where should we move the center? That's the first point. And where should, instead of having the x direction going like this, which direction should we choose for the x direction? Yeah, parallel to the function here. So if we choose these as our coordinate systems, so here's our u, and here's our v, whose theorem is this now? This is Rolle's theorem. So the mean value theorem can actually be reduced to Rolle's theorem if you're just willing to go like that. And so you just need to transform your function. You need to take your function and subtract things off so that you map this point and this point so that they now rotate down here and just see how things propagate. But this idea of trying to reduce simple cases, build your intuition there, and then extend, this is an extremely valuable idea. It's often hidden and the mean value theorem actually is essentially the same as the special case of rules. All right, so again, we did a lot today. If this is not how you want us to be, if there are things that were in the lecture that you wanted covered, let me know. It's we can either meet one-on-one, or I can try to work some of them into Friday's class. I'm going to try to have a couple of lectures in advance posted online with the homework. So I think the first 6 homeworks are now posted. If you want to move ahead, that's fine. I'm trying to have the homework lagging a little bit from the lectures in terms of when things are due, so that you are not in a terrible position of, so we learned this stuff on Wednesday and now I have to hand it in on Friday. This is why there was no homework due today, to just give you a little bit of a push on material. All right, have a good day.